Hello and welcome to a video about a capacitor charging. This is a very popular topic in AP Physics C, and it's an interesting one. First, I'm going to give you the equations, if that's all you're here for. Then I'm going to give you an overview of the process. We'll derive the equations. You have to be able to do that in the exam. And we'll talk about tau, the charging time, discharging time. So if you're just here for the equations, here you go. The voltage of the capacitor versus time, the charge of the capacitor versus time, and the current flowing in the circuit versus time. So what's going on? You have a battery, you have a resistor, so far familiar. Current's going to flow, but what's different here is there's a capacitor. Now, initially this capacitor doesn't have any charge, it has no electric potential, and the current flows exactly like it would if there was no capacitor there at all. In fact, the value of this I naught is going to be the same as the battery voltage divided by resistance. But as time goes on, what's going to happen is that little charges are going to build up on this side positive and on this side negative. You have a decent sized, whatever that means, battery. I'm going to draw it as a physical shape. As this capacitor gains charge, it's also going to gain a potential difference in the opposing direction. Now, in the beginning, that's a fairly modest potential. It's not that it is a battery. I just want to show you that it has a potential that is going to sort of counteract. It's going to push in the opposite direction. The battery is trying to push charges. Now, remember, the definition of capacitance is charge per potential difference, or charge per volts. So how much charge do you need to get a given voltage in a capacitor? And because that's opposing the direction of the voltage of the battery, that's going to cause this current to decrease. So this I, instead of being I naught, E over R, is going to be somewhat smaller. How much smaller is going to depend on the actual amount of charge that's on the capacitor. And as time goes on, that current is going to get smaller and smaller and smaller until eventually what happens, and what ultimately stops the current from flowing at all, is that this battery, it's not really a battery, but this capacitor has a potential difference that's equal but opposite to the potential difference from the battery, the E, and that's going to make your current go all the way down to zero. We're going to come back to this, but if you want to get a sense of what's going to happen with the voltage across the capacitor, in the beginning the voltage is zero. But as time goes on, the capacitor charges, the voltage increases until eventually, sometime later, we'll get more specific about that later, it's going to reach the potential of the battery. Now, if you look at the current, I'm going backwards in time now here, and you look at the graph on the right, in the beginning the current flows just as if there was no capacitor at all. But as time goes on, it gradually approaches zero. The current will stop when the capacitor... Take a look at what's going on. In the bubble on the right, you can see what we're going to end up with for the results. And I like to show you that ahead of time because it helps you see why we're going where we're going. And if you've done this in mechanics, you've probably seen a very similar relationship with terminal velocity, at least when terminal velocity is proportional to velocity, much like current is proportional to resistance. The math is the same. So as the current leaves the battery and charges up this capacitor, there's a voltage drop from charging up the capacitor. Now, recall the definition of capacitance is charge per voltage. How many coulombs of charge do you need to get a particular voltage? So as the current goes around, we're going to want to think about this in terms of Kirchhoff's law. As you go around a loop, the energy must add up to zero, or the potential drops must add up to zero. So if we take them one at a time, you can start with the battery, E, minus the voltage of the capacitor, minus IR equals zero. Now, I'm using little I here because the current actually changes with time. The current's going to decrease as time goes on. The reason being, it's getting harder and harder to squeeze more charge onto that capacitor. Now, the voltage of the capacitor can be rewritten as Q over C, or I'm going to write it as 1 over C times Q. And the I can be written as dq dt. Now, it's not as important for the charging of a capacitor, but the current here is going to be positive. As dq increases, the current is going into the capacitor and through the resistor, so the sign's consistent there. Times R, that's going to be 0. Now what you're going to do is you're going to watch me do some math, if you'd like to, or you can hit the fast forward button. It won't hurt my feelings. First thing I'm going to do is I'm going to multiply across by C. So this becomes CE minus Q minus RC dq dt still equals 0. I'm going to bring the CE and the Q over to the other side, so this becomes minus RC dq dt equals Q minus CE. And if you continue playing along, you can see you've got dq dt, so you've got stuff with Q in it and stuff with dt in it. This is going to be a separation of variables thing. So what I'm going to do is I'm going to bring the Q minus CE over to the same side as the dq, so that's actually 1 over Q minus CE dq equals, and I'm going to bring the dt over to the other side, and having done this before, it's convenient to bring over the minus RC, so that's going to be minus 1 over RC. Now at this point you have two different things that we can integrate. We can integrate the dq stuff, and we can integrate the dt stuff. Limits are important here, so we're going to integrate from when there's no charge to when there's some final charge, or Q of t. I'll use capital Q. You're going to go from some initial time times 0 to some final time I'll call capital T. Now on the right side, that's easy. The integral of dt is just t from capital T to 0. You wind up with minus t over RC, where t is the time at which you want to know the charge. On the left, you may recognize that as like a 1 over x relationship, and the integral of 1 over x is ln of x. So here what we're going to do is we're going to take the ln of Q minus CE, and we're going to evaluate that from 0 to capital Q. So as we keep going here, if I plug in capital Q, this becomes the ln of capital Q minus CE minus the ln of 0 minus CE equals negative t over RC. You may remember your log rule. Subtracting is the same as the ln of Q minus CE over minus CE equals negative t over RC. Now you can break that ln apart by raising both sides to the e, meaning the left side here becomes Q minus CE over negative CE, and on the right we have e to the negative t over RC. Now for convenience, I like to bring the negative sign to the top, meaning CE minus Q over CE, which is the same as 1 minus Q over CE equals e to the negative t over RC. And we want to get Q by itself, so I'm going to bring the e stuff over. This winds up being 1 minus e to the negative t over RC. It's really starting to look like that stuff at the top. And on the right here is Q over CE. Solve for Q, and you get Q equals CE, which, by the way, is the final charge, capacitance times voltage. It's just some fraction of that. That fraction of it is 1 minus e to the minus t over RC. Notice, when t is 0, you wind up with 1 minus, e to the 0 is 1, so you wind up with 0. You wind up with no charge, which is exactly what you expect. So we've got our charge equation, and then if you wanted to know the voltage, well, capacitance is Q over V, so V is just Q over C. Well, you take this, it's almost exactly the same. The voltage across the capacitor at any point is the battery voltage times some fraction. And that fraction increases with time. because as you have time go up, it winds up being 1 over. I was just saying that as time goes on, you wind up with getting 1 over e to a bigger power, which is making it smaller and smaller, so it approaches the battery voltage, which is what you'd expect. Now, as far as the current through the resistor, remember, this is the voltage of the capacitor. The voltage of the capacitor plus the voltage across the resistor has to add up to the voltage of the battery. So if I wanted to know the voltage of the resistor, it would be simply E times e to the minus t over RC. And the current would be that over R, ER over R, times e to the negative t over RC, which, by the way, is the same as some, just make that easier to read, some fraction of I naught. So it's the same as I naught times e to the minus t over RC. Now, if you look, these are exactly what we expected to get based on these formulas that we had before. You talk about the time constant, RC. If you multiply the resistance times the capacitance, the units actually work out to be seconds. But what does that mean? Well, the formula clearly is an exponential, or it has an exponential in it. So when we say something has gone 1 tau, or 1 t, 1 RC, what that means is you either have 37% or 63% left, depending on what quantity you're talking about. So the charge increases as time goes on. At one time constant, in other words, when the time that's elapsed is 1, whatever RC is, you're going to have 63% of the charge that the capacitor is ultimately going to have. Your current, however, will be 37% or 36.79%. Where did that number come from? That number came from 1 over E. So this is 1 over E. This is 1 over E squared. This is 1 over E cubed, etc. It goes on. This column is 1 minus that. So the capacitor technically never gets fully charged, but it sort of asymptotically approaches a value. I've heard tossed around, a lot of people consider it fully charged at 5 tau values. I'm not sure. I don't really know how you decide a capacitor is fully charged. But a common question is, how much time does it take to get 37% of the way charged, or 63% of the way charged, or something like that? When you hear that number and think, that is such a random number to use, it's not really random. It makes a lot of sense, because e to the 1 is easy to compute. E to the 2 is easy to compute. It's an amount that's just agreed upon, that we can compare capacitors and charging and discharging times. So once again, here's a simulation I made in Excel. And if you notice, I've been toggling on and off this display as a fraction button. This is the raw time in milliseconds. So you can see the charge and the voltage going up with time and the current going down with time. Or it's useful to display it as a fraction of tau, meaning is it 1 time constant or 2 time constants, etc. Of course, that's not working for me now, but there we go. And again, when you look on the graph, for example, of voltage, when you go 1 time constant, 1 tau, the voltage is at 63% and the current is at 37%. So back to the beginning here, what's really going on with these RC problems when they're charging or discharging is that in the beginning, the capacitor offers basically no resistance whatsoever. I should say no potential difference, no voltage. In the beginning, it acts like a wire. But as more time goes on, this acts almost like a battery with the voltage in the opposing direction, until at some point, the capacitor has so much charge, its voltage is equal to the battery, but in the opposite direction, and no current flows. course, you never technically get there, just asymptotically gets there. But that's what's going on in these problems. So hopefully this video made sense to somebody.